on. This one you can put anywhere you find
yes.
comfortable for you.
Okay, there.
Here.
Yes.
Yeah,
pointer.
Laser.
Yes.
4G backward.
Okay, perfect. Thank you. So, once again, just for me to be recorded, good morning. I feel to be the most exotic person here because of distance. And, well, I will tell you today a few words, let's say a few introductory words on statistical downscaling. The lecture will be a bit interdisciplinary because I included also a short excursion to the history of statistical downscaling, or even, I would say, a prehistory. So I come from Prague, and you may know International Journal of Climatology, one of the high-quality international climatological journals. It's not just by chance that it's here, because I am its chief editor of this journal. So, if you have a good paper, please send it to our journal. If you have a bad paper, please send it elsewhere. Thank you. Thank you for your cooperation. And so, let's go. Let's start with history. Early history of statistical downscaling goes back to 1950s, 1960s, and the early developments were done within the numerical weather prediction. Because at those times, the numerical weather prediction was just in its beginnings. The prediction models were able to forecast successfully just the upper level flow, but had problems with correctly predicting what's going on the surface. But it's, of course, surface temperature, precipitation, these variables which are of interest to anyone. So in this case, statistic was ready to help, and various methods were developed to relate the surface weather conditions with a large-scale circulation. At those times, this kind of task was called specification. Specification of surface temperature from mid-tropospheric flow. The pioneering work in this direction was done by William Klein. It was an American, and I think we can consider him as a kind of grandfather of statistical downscaling. He published many, many papers on the same topic. It's incredible. Yeah? Just we have a large-scale flow and how to get surface temperature, precipitation, or anything. The history came again in a very similar situation, but later, 20 years later, already within climatology. We've had GCMs, which were general circulation models at those times, not global climate models, but because the models were able to simulate only atmospheric circulation, basically nothing else. So the models were again able to simulate the large-scale flow, but not able to simulate successfully the surface small-scale features, the surface variables. Well, and this issue basically, or this fact is still valid today. The global climate models can simulate large-scale upper air features successfully, but less so surface climate. That's why we have to run the regional climate models or statistical downscaling. The first attempt, as far as I know, to bridge the gap between the large-scale and small-scale, local-scale climate was this paper published in Monthly Weather Review in 1984, a paper by Kim and others called The Statistical Problem of Climate Inversion. In this paper, the statistical relationships were looked for between large-scale and local temperature and precipitation. And this procedure was called climate inversion. Apparently, this term, the coining this term was not successful because it hasn't been repeated since those times. Nobody has used this term climate inversion after that. So this was the first attempt in 1984, and then further attempts came in late 1980s, 1989, 1990. Dan Wilkes and Tom Carl published their papers on statistical specification of local surface weather elements and so on. These papers already presented what we call statistical downscaling today, the basic methodologies, basic principles, but the term downscaling hasn't been used or wasn't used in these papers. I tried to find out who was the first to have used the term downscaling, but I wasn't successful. I don't know. Because even in the paper, many times cited paper by Filippo Giorgi and Linda Mearns, published as a review paper of how to approach to regional climate change and its simulation, published in Reviews Geophysics in 1991. I was surprised that the term downscaling was not used in this paper. So I don't know who is a real father or mother of the term downscaling. I have no idea. That's if you know, or if you think you know, I'll be lucky if you tell me, because, well, the term appeared suddenly from somewhere and started to be used as something self-evident, but where it came from, I don't know. So just a side note, at the same time, when the first papers on statistical downscaling, although we didn't know at those times that it was statistical downscaling, were formulated and developed, also the first attempts to run regional climate models beyond their predictability limits, which is just the beginning of regional climate modeling, were done by Filippo Giorgi and Dickinson at the turn of 1980s and 1990s. So, current state, from history to the present day. What is considered statistical downscaling or empirical downscaling today? The meaning of downscaling has broadened recently, and the term downscaling, of course, includes the meaning of reducing the scale, from large scale to local scale, downscaling. But currently, many different methods are referred to as downscaling that even don't bear this essential meaning of increasing the scale. So also procedures like stochastic generators and approaches used to correct statistical distributions at local scale, known as bias correction or MOS, model output statistic-like approaches, are under the roof of downscaling or statistical downscaling now. This may cause some kind of confusion because different people understand different things under what downscaling is. So my feeling is that using such a dynamic use of terminology is not very useful, and I will stick to what I can call a classical statistical downscaling, meaning downscaling. I will explain what it is. Classical statistical downscaling, that means PP methods. What is PP methods? It's a terminology coming again from numerical weather prediction, when some post-processing of the prediction outputs were necessary to get a true local scale forecast. And this is PP means perfect prognosis. That means we assume what a model produces is correct. So the principle is relating what the model simulates well, this large scale free atmospheric variables in the case of using statistical downscaling in climate change research with a local scale, and training these statistical relationships, which is sometimes called transfer function, to train this transfer function on observed real data. And then when we find what the relationship is, when we find the regression coefficients and so on, then we can apply it to global climate model output. So first we develop or train the statistical model on the observed data. Then we apply it to global climate model output for current climate conditions. Then we apply the same transfer function to global climate model around for future climate conditions, and then the climate change, that is what is interesting for us, is simply the difference between the downscaled values between the future and current model runs. It can have many modifications, this approach, but this is the basics usually applied. Well, let's proceed further. A few words about what I consider to be, or what I call to be, a paradox of statistical downscaling. The statistical downscaling models are typically fitted to the variability on time scales that are much shorter than on which the climate change proceeds. We fit the statistical downscaling models on a daily scale. But what we care about, what is important, what is our objective, is to describe the decadal change, that is trends, long-term changes. But this is a simple illustration. This is, let's say, the observed variability. Yeah, some shorter term variations superimposed over a long-term trend. Then we run a downscaling model, statistical downscaling model, and we get such a series. Very good fit on a short time scales, but a different trend. So we can think we are very successful. The correlation 0.95, that's great. Well, but we are not winners, we are losers, because we are not able to describe the long-term trend that is of interest to us. So something doesn't work well. This directly implies one fact, that the degree of fit with the observed data on a short-term scale, that is of daily values, or I don't know, of monthly values, cannot be the only criterion for the selection of the downscaling model, for finding the best downscaling model that we will use. We must find another criteria that will also take into account the long-term development, the long-term behavior of the data. So illustration of this paradox comes from now already a bit old paper, but well, the results are valid. So it's my paper in Journal of Climate 14 already years ago. So I used simple linear statistical downscaling methods with different settings, with different numbers of predictors, with different ways of how to handle principal components and so on, with different predictor sets. It's not so important. It was applied to one global climate model in Central Europe. Sorry, well, Central Europe is far away from here, but it's quite natural for me to do my exercises in Central Europe. For temperature in winter, winter is December, January, February. This is what I must stress here, yeah, because I get confused with your winter and your autumn. Well, it needs some thinking. This is result. What's shown here? Every row corresponds to a single method, statistical downscaling method, and for every method you can see a box and whisker plot showing the range of temperature change values over the 39 stations in Central Europe. And just to have an idea, these different large groups are for different predictors. The smaller groupings are for different methods, and within the groupings, different numbers, different parameters are used, different numbers of principal components, canonical correlation pairs, and so on. So basically, it's different methods. And you can see, well, that the difference of the expected temperature change, future temperature change, is quite wide. Yeah, it's from something like ½ degree Celsius to over 8 degrees. Well, it's not a very successful result. So we arrived at a philosophical, statement that we know that we don't know anything. Yeah. It's not only the amplitude of temperature change that differs, it's also spatial patterns. As you can see, two different methods over Central Europe. You can see Germany here, and it's Czechia, Slovakia, and so on. For one method, you can see maximum expected warming somewhere in the center of the domain. Another method gives totally different spatial pattern. Well, also the elevation dependence is different. We have 7 variants of statistical downscaling with canonical correlation analysis, from 1 to 7 canonical correlation pairs. And while for some methods there is no actual dependence on altitude, we have stations in Switzerland and Austria, really from the lowland stations to a mountain station of over 3,000 kilometers. There is no elevation dependence at all, or there is a considerable elevation dependence. Oh, thank you. So, what's the truth? So, all the models are good in terms of fit to observations. For example, in terms of root mean square error, correlation, and so on. Some of them are marginally better, some of them are worse, of course, but all of them can be considered good. But the mean temperature change varies in a very wide range. And other aspects of change, of temperature change, also vary widely. So how to decide which model to prefer? There are two ways how to go out from this paradox. One is the a priori selection of predictors. We must think which predictors to choose, because we must choose the predictors that really carry the information on climate change, even though the predictors may not be the best in terms of the fit to observations. And the other way to proceed is to look at other criteria than only the fit with observations. We should also look at how the methods are able to reproduce the long-term trends, and so on. So it's possible to validate trends as a possible remedy to the problem. This works, however, only if the same mechanisms stay behind the trends in the past, for which we have the downscaling trained, and for the future, for which we are looking at. Also, it's possible to check whether the downscaling methods are able to simulate contrasting climatic states, like cold versus warm, dry versus wet. And also, it's good to look at at how consistent are the downscaling outputs with the driving global climate model. Of course, the global climate model may be wrong. And it's the reason for us to do the downscaling, that the global climate model doesn't simulate the local climate well. But there must be some consistency. If you get, I don't know, 4 degrees warming in global climate model and 2 degrees cooling in your statistical downscaling model, then probably something happened and you must check what happened. Well, the last few comments now regarding the relationships between statistical and dynamical downscaling. I must say, well, that I didn't intend to say that statistical downscaling is bad. It may look so after showing these contra-intuitive examples. But if you know what statistical downscaling is able to do and what is not able to do and how to work with it, then you are likely to be successful in the application. There is, I think, not only my feeling that statistical downscaling is looked sometimes at as something simplistic, inferior, not as good as other approaches to downscaling. Because, well, it's a matter of fact, and also yesterday Maria Laura mentioned it in relationship to CORDEX, that, well, in large international projects, statistical downscaling, if it appears, then it's just treated as an appendix, small appendix to regional climate modeling efforts. But, on the other hand, the few comparison studies that have been made, the few comparison studies between the performance of the dynamical downscaling by regional climate models on one side and statistical downscaling models on the other side, these few comparison studies have shown that these two approaches have a similar performance in terms of any criterion you can think up. Well, what comes now? Just an example of how the observed time series are reproduced by regional climate models nested in reanalysis, which can be expected to be very good, and statistical downscaling models also driven by reanalysis. The example is, again, sorry for that, for Central Europe. Now it's a really very Central Europe. It's a former, we called it a former, it's Austro-Hungarian domain. Yeah? We had an Austro-Hungarian empire in Central Europe before the First World War, for a long times ago, and this is an example of such a domain. You can see, well, this is Czechia, Slovakia, Austria, and Hungary. What you can see is correlations with observations for minimum temperature in Northern Hemisphere winter. On the left, two regional climate models, and on the right, 5 different statistical downscaling models. Don't look at this one, it's a strange model, but the redder the color, the better agreement in terms of correlations. So the comparison is that, well, the dynamical downscaling and statistical downscaling performs almost equally. But if we look at the temperature at daily maximum temperature in summer, then the regional climate models on the left become obviously inferior, much worse than the statistical downscaling models. Well, this doesn't mean, I don't want to say that statistical downscaling models are better, but it's just an illustration of that not always the more complex, more complicated methods gives better results. Well, similar for temperature skewness and, well, precipitation. I will come to the end of the talk, of the presentation. I would like that you agree with me that the statistical and dynamical downscaling are not competing with each other, but rather are complementary. Yeah? Because both of these techniques have their weak points. The problem is that these weak points are frequently not admitted and not reconciled by their users. So my advice to you is that if you apply any of these methods, then please be aware that your method is not perfect and that there are other methods. And you should think of your method just that it's not the only one method, the best one. Just you must be aware of some limitations, some conditions for its correct use. And I think that's all. Yes, that's all. So, thank you for your attention. Yes, microphone for you. And water for me.
To share at this time of the morning. Okay.
So regarding your figure in the beginning, comparing a trend.
Yes.
Regarding that context, would you compare, for example, this study, the final slides in terms of the trend?
You mean, yeah.
Just beside the correlation analysis, do you have any comparisons?
Will you be here tomorrow? Yes.
Yeah.
You will see the comparison of trends. At least I hope that I will I have it in the other presentation that I'm going to have tomorrow. Yes. Neither of these models is able to reproduce trends correctly because of the inherited problems with trend reproduction in their analyses. Yeah, so that's my preliminary answer.
That's it? Okay.
Mine is just a comment, just out of clarity. So I agree with you that the two things have to be looked as a complementary. But let's say the problem we have, at least within the European community, with the statistical downscaling community, is that although we included this in the CORDEX group and we made a lot of effort to understand ourselves how the two things could be complementary. What I lack at the moment, and I don't think because I don't read enough paper, is the real application of this statistical downscaling method within the CORDEX context. Because beside CORDEX Africa, in which they did something on statistical downscaling, but then in every, including the FPS that we are running in Europe. So this community is a little, let's say, vague. I mean, there is no, at least for us, for the other, there is not a clear plan how they are going to bridge this gap and use the statistical downscaler. And the other thing is not clear to me is, okay, I agree beside the debate that if you do the statistical downscaling on temperature and precipitation, then the two things are uncorrelated, but you can find better method like many other that have been developed to try to bridge the gap. But the issue is when you go on a climate change projection, do you, and this is really a question, do you know any work on statistical downscaling that show the added value of this method in climate change projection? Because this is a difficult task also for us, to show. But at least we can find something on like process, like high topography, land surface interaction, land use driven change. So there are some studies that show, but I struggle to find this. I mean, it's easy to be good when you have the observation, but then afterwards, how consistent are this method in a projection?
I think this is a topic for a long discussion for the rest of this meeting.
I know, but it's just out of completeness, because nobody wants to say that this method is not useful, but the things that lacks at the moment, I think it's a little of...
Yeah, I fully agree with you. Well, I was part of some efforts to form a group of statistical downscalers within CORDEX, but yeah, Mariella was there as well. Apparently it was not a successful attempt. Maybe one issue is that the structure of CORDEX Europe and CORDEX, I don't know, South America and CORDEX Southwest Asia, is something what is necessary for regional climate modelers. Yeah, because regional climate models need to have unified research domains and so on. This is not what statistical downscaling needs. Statistical downscalers just need data from some region, and well, if the region is so small or so large, it doesn't matter for many methods. So maybe the structure is not what statistical downscaling could fit well into. It was my impression in the, I don't know, few years ago. Regarding your last comment, the application to future climate, well, I think there are, I don't want if numerous, but there are studies linking or linking future climate developed by statistical downscaling models or weather generators, which is
Not
also
sure they are,
yeah,
but I
yeah,
mean
yeah,
some study that showed that.
that showed
They work.
added value. Yeah.
Yeah.
Huh?
Yeah. But anyway, I just want
I
to
will think of it.
But within the EuroCordex, there is a whole statistical downscaler group that it's there. It's included, fully included since 2 years, and I mean they are always there. And but still, it lacks a little bit of what should we expect from them? Maybe it's a little less. This Cordex Africa has something more advanced because there is Bruce Hewitson,
yes.
and then okay, they have something a little more, but still, we are waiting something.
Yeah.
Regarding the added value issue, I think statistical downscaling would be more important rather than comparing two different downscaling, but I think it will have more crucial important applying a bias correction of statistical downscaling to the boundary conditions and then run a regional climate model and to compare without any correction or correction, then I think that would make sense rather than comparing two different mechanisms. I know some papers of some groups in Australia or in Europe, they combined both methods, but first apply a bias correction method to the boundary conditions and then run the model and then compare the result with that bias correction, then that would make sense.
Yeah.
Rather than
for sure, yes. I know there are these attempts, efforts go in this direction. Yes, I know. But bias correction is, in my eyes, something different from statistical downscaling. It's a post-processing of regional climate outputs, basically, to localize them or to correct them for the real climate and to localize them to any given location. Yeah? Because, I didn't say that, I feel that still, even when regional climate models are run in quite a high resolution, their outputs is still not local. Yeah. It's still a grid box output. And statistical downscaling is a technique that produces, if you want, a real local output. So this is what I see as its advantage. But with the growing resolution of regional climate models, this advantage is just slowly disappearing. Yes.
I would see it more complementary, no? Do you agree? I mean, we could do things together, but still the regional, climate, the dynamical downscaling has a finite resolution, and we will never be able to go to 100, 200 meter resolution.
Probably.
Not in this life. So I think I would rather see this as a complementary effort, and this is the reason why we have this task force in other Cordex region. But yeah, I hope it happens.
Okay. No. Okay. Okay. Thank you, Radon.
Yeah, it was a pleasure. Thank you. Doesn't want. Oh. Oh. I will leave you something here.
Hello. Well, now we have the talk of Rosemary Porfirio da Rocha. She is a professor here at the University of São Paulo. Well,
thank you,
thanks,
Maria Laura.
Rosemary.
Good morning, everyone. Now I will return to regional climate modeling applications in South America. I will to do a review of some studies that our group of the University of São Paulo is doing, and looking for from regional to local features of climate. Basically, my talk will be concentrated on RegCM, regional climate model results. I am planning to show some simulated the regional and the local features of climate. Here is a table that I take from Ambrise et al. 2018 papers, showing that regional climate modeling started in the 90 years in South America. The first studies occur using ETA model and GFGLE, and after the paper of 2001, which RegCM model, I think that is RS, regional spectrum model. And with RegCM, the first papers start for South America domain in 2003. These first studies are looking for evaluate the performance of regional climate models in capturing the observed mean features of the climate. These first studies are individual models looking for reproduce the local climate, the observed features of local climate. This table also is from Ambrise et al. Here we are listing 4 main projects that use the regional climate models over South America. This one is a Brazilian project. We used 3 models, ETA, RegCM3, and the Precipitation model for downscaling regional climate over South America and the climate change. In this one is there is more 7. This is a collaboration. CLARIS, the first phase of CLARIS, that was a collaboration between South America and Europe to downscaling regional climate over South America. In 2009 until now, we have the CORDEX. Many people talk about this here. In CORDEX, there are many models to be being used to regional climate models, where the regional climate model is together in this project. And the second phase of CLARIS that starts in 2008, you have 7 models that are used to downscale present and future climate over South America. This project used 7 models. Here is only a picture showing the 7 regional climate models nested in 2 CMIP3 GCMs. In this case, we use the A1B scenario. Here is a mix of the individual simulations. This is the observation, and this one is the bias from precipitation. This is the annual bias. You can see that there is a general underestimation that of the models of annual precipitation over South America. And the RegCM ensemble mean is this one. We can see that the use of the ensemble mean reduces the bias in most of the regions of South America. This picture is showing the trends. Here you can see that blue is the trend of weather condition. This model are showing weather condition. This other one showing dry condition in this part. In this one is the ensemble mean. So you can see general, in ensemble mean, you can see the general trend of negative rainfall over center north of South America, and the weather conditions over southeast of South America. Well, the CORDEX, inside the CORDEX idea, we worked together to develop the CREMA project. That was a CORDEX RegCM for hypermatrix experiment. It was a collaborative experiment designed to provide mini ensemble downscaling using different physical configurations of the regional climate version 4, nested in different CMIP5 GCMs and scenarios. This is a picture showing the subdomains that CREMA phase 1 experiment did the downscaling. Basically, you have a 34 scenario simulation from 17 to 2100 over 5 CORDEX domains, which RegCM for driving for 3 GCMs, 2 scenarios, RCP 4.5 and 8.5, and different physics schemes. For South America, the ensemble is synthesized in this table. The domain is this one. We use the 50 kilometers of horizontal resolution, 2 land surface schemes, the CLM and the BATS, and with different convections. Which is CLM, we use the Emmanuel convection, which but you use a mix of convection, Grell over the land, and Emmanuel over the sea. Here is the table, for example, for 4.5 scenario, you have only the simulation that was nested in RegCM 2 global model. These simulations, for 8.5 scenario, you have 2 simulations using RegCM 2 and 2 simulations, one using MPI and another one using GFDL. These simulations are available in this link, the air temperature and the rainfall, the monthly mean values data is available. Francesca, you talk about how to use this data.
Not yet. In the lab.
Okay. So I will show some results of CREMA phase 1 South America projections. We used to look in the trends, the interannual variability, climate change impact on precipitation over La Plata, Amazon and La Plata basins. We used the CREMA to look at the frost events over Peruvian Andes, to look in cyclones, in the thermal comfort in São Paulo, and the other studies. Here is only for, this is for summer. We used many observed data to construct this picture. It's an ensemble of observation. This is the ensemble of regional climate model. This is the ensemble of three global models. You can see here the main features of rainfall are present in both the regional, the global model, but you have a more intense rainfall here that is more, a little bit more close to the observation. Here is the trend for this is for summer. We can note that there is a great agreement between here you have the RCP 4.5 in this column. This one is RCP 8.5. And this one is the RCP 8.5 for global models. This is for the regional climate model. This one for regional climate model. In this line, you have the near future trends. In this one, you have the far future trends. You can, there is a general trend of weather condition over this part of South America, and in near future the trends are not so intense, and a general decrease of rainfall in the north part of South America. In far futures, the trends intensify. You have this signal is was observed, this signal of a decrease of rainfall over center and north of South America, and the increase over this part was noted also in CMIP3, in global regional simulation of CMIP3. This one is the time series. The red is the mean of the ensemble mean. This ensemble mean includes the regional and the global simulation. We can see this is for La Plata Basin subdomain. This one is for the Amazon subdomain. Here is for summer, Austral summer, Austral winter. You can see that most of projections indicate increase of rainfall in summer over La Plata Basin. But you have a big spread between the models in the trends. But for winter, the signal is not so clear. We have models that indicate increase, and other models that indicates. This one is for this is the global GFDL model that is showing trends, very intense negative trends. So the signal is not so clear for the winter. This one is the observation, the black line. In Amazon, we have a large spread also. Some models showing a very different behavior of the trends. And for summer, you have a small trend of increase of rainfall. Here is more or less 5%. It's too small. But we have more than one time a very spread between simulations that is bigger in summer than winter. For winter, we have a general trend of decrease of rainfall of Amazon in these simulations. We look at also in this simulation the signal of in rainfall during the spring, between the difference between El Niño and La Niña years. We use the SST in the Niño 3.4 to define El Niño and La Niña years. You can see this is the observation, this is the regional climate model, this is the global model, and the signal, during El Niño you have more rainfall over southeast of South America. It's this place that is here. This signal is apparent in global, in the regional, in the signal of the regional and the global model is similar to the observations. This is the trends, how you behave this signal in the climate, in the future climate. This is the near future, this is the far future, this is the RCP 4.5, regional, global, RCP 8.5, regional, global, and we can see that the signal is similar in the future to that of present climate. However, we note that the signal mostly here, the positive rainfall associated with Niños, El Niño, is weaker in the future than in present climate. This is likely connected with the GCM's projection of ENSO signal displaced to central part of the Pacific Ocean. We use the Kramer simulation to look at the thermal comfort in São Paulo megacity. We look only in RCP 8.5 scenario. Here you have the trends, the future minus present climate. This is the temperature. Here is relative humidity. Here is the thermal comfort indices. This is the difference between this and this one. We can note that in the future the projections are indicating the increase of the temperature, decrease of relative humidity, negative, and this increase of temperature is more or less compensated by the decrease of the relative humidity. And so the effect, the comfort trend, the trends of thermal comfort is not so big in this area. When we did the difference between this and this, we noted that São Paulo is between, here is São Paulo megacity. You can see that here you have the positive trend, here you have a negative trend, and São Paulo is between both. So with this study, we concluded that we need fine resolution projections to better understand the local climate change impacts. Now, after I am confused because we looking for frost days over Peruvian Andes in these three regions, north, central, and south parts of the Andes. We look at frost days, looking the minimum temperature smaller than 0 degrees. We look for JJA in the present climate and also in future climate, but I will show only the present climate. Before to find the frost days, we applied perfect prognosis statistical, I don't know if bias correction or downscaling, because to correct the minimum temperature from RegCM 4 from Crema simulations. Basically, we used the multiple linear regression using area interim loss predictor. Here you can see this is the annual cycle of air temperature, minimum temperature for this region. We used 3 observations to construct this annual cycle. Here is the local observation, station observations. Here you have CRU observation, and here you have the simulations, 4 simulations. We are comparing with 4 simulations. One simulation that was nested in a perfect boundary, that is area interim. One we using hydrogen, another one GFDL, and another one using MPI, was lateral boundary. Here is the Taylor diagram for this annual cycle. If you look, for example, here is CRU. You can see that the correlation is high for annual cycle, but you have a big warm bias in the simulations, and a big cold bias in CRU observation. This is the annual cycle after the bias correction. We can note an improvement in the amplitude of the annual cycle of minimum temperature, and a decrease of simulation warm bias after bias correction. After bias correction, you look for minimum temperature less than or equals 0 degrees. And here you can see in the trends of frost days for summer, autumn, and the winter, spring. Mostly we can see that there is a trend, a negative trends of frost days in summer and the autumn, but in winter there is a small increase of frost days, and in spring a small decrease of frost days. Here is the annual cycle of the frequency of frost days. This is from local observation. And here you have the simulations. We can see that the simulations can reproduce the form, the pattern of the annual cycle, but for example, there is an underestimation of frost days during the winter time. By comparing the simulation, you noted a small overperform of a regional climate model when the simulation using GFDL and the MPI was lateral boundaries. This can be due to the fact that normally hydrogen simulations are warmer than the GFDL and the MPI. Michele shows yesterday the analysis of cyclogenesis climatology over South Atlantic Ocean. You skip. We are now doing the same, looking for cyclones in the simulations that use GFDL and the GFDL and MPI. Here is the observation. Here I'm showing only present climate. This is an interim. This is the RegCM using hydrogen. This is using MPI and GFDL. We are doing this to looking for different classes of cyclones over South Atlantic Ocean, mainly to look in the subtropical cyclones. Well, now I will do, there is a CORDEX phase 2 plans, and to the paper of Gutovec et al. 2017 did a general view of RCP CORDEX 2, and two questions are important for this phase. CORDEX core framework, where we have some groups doing regional climate downscale with horizontal resolution between 10, 20, but 10, 25 kilometers using a set of global models. Erika talked about this yesterday, which RegCM, this will be part of CREMA phase 2. And Maria Laura and Silvina talk about the flagship pilot studies that to address specific scientific questions of methodological and regional relevance. We are working together, Maria Laura, in the flagship of South America to look at extreme precipitation events in southeast of South America, a proposal for a better understanding and the modeling. This is the title. So in this line, you are looking for some analysis of grid resolution impacts on simulated climate. I will show two examples before the flagship. Here we did a simulation, two simulations with regional climate version 4, using this domain and the grid space of 15 kilometers, and this one using 20 kilometers. We did the simulation to Austral winter season, June, July, August, September. After we compare the simulation with IAG station, we are more or less here. IAG station is here, and here is the park that IAG station is inside. Here is the city. There is a park, and the IAG station is inside this Science 132 year. It's more than 80 years of observation in this park. Here you have the daily mean temperature time series. Here you have the observation is in black, the simulation with 15 kilometers, with 20 kilometers, the NCEP reanalysis that was used was boundary. We can see that the regional climate reproduced the observed high frequency temporal variability of air temperature. We noted that there is an added value from RegCM simulations. The statistics that we obtain with RegCM simulations shows that the simulations are close to the observation than NCEP reanalysis. And we noted also that high resolution can improve a little bit more the statistic. You have a great correlation, smaller root mean square error in the closer the standard deviation. This is for air temperature. Here you have the frequency of fog events for 2003, 2004. And here you have the model can reproduce the more or less the month-to-month variability of fog events in both 2003, 2004. Here is we use the fine resolution simulation to construct the anomaly of relative humidity for days with fogs in São Paulo city. You can note that during the fogs you have a positive anomaly of relative humidity in all this region. São Paulo is more or less here. And a negative anomaly of specific humidity in the south of the São Paulo. This is very, very an old cyanotic pattern. When you have anticyclone here, and you have the northwesterly wind flowing from the ocean and transporting moisture to this area where is the city. I will show rapidly the grid resolution impacts more on time. In this case, we did 4 simulations, one using 100, another one using 50, another one using 25, and the last one using 5 kilometers of horizontal grid. The coarse resolution, we use T-domain. The high resolution, you use a small domain of 5 kilometers. Here you have, we can use the hydrostatic version. In this one, we use the no hydrostatic version. Here you can see how the land use changes from coarse resolution to high resolution. Here is the annual mean rainfall. This is from CPC. There is another Uni observations. Climate Prediction Center observations. This is the observation from rainfall from tree. Here is the scale. Here you have the simulation as function of the surface scheme. And here you have CLM. In this line you have BATS. Here you have the rainfall for 150, 25 and 5 kilometers. There is a small, if you compare in details, you can see a small great agreement with observation when you use BATS. in high resolution, this column, for example, to localize this more intense rainfall, if you compare with the spring, you have a little bit more better performance from BATS than CLM. But more or less, all simulation, when you go in high resolution, you can see, for example, some patterns that here that are not so clear in coarse resolution simulations. So we can note some improvements of an all cycle of rainfall in spatial pattern of simulated variables in fine resolution experiments. In both, in CLM and BATS, we consider this added value to coarse resolution simulations. I will show now some local or some mesoscale circulation over the southeast of Brazil. Here I am showing only a part of the domain. Here you have in colors, you have the annual mean rainfall, and you have 10 meters wind circulation in arrows. Here is São Paulo. It's like a dog. The head of the dog. This is São Paulo. This is the big metropolitan area. Here you have more or less 20 million of people living. You can see that the main patterns of the mean circulation, for example, the northwesterly wind, the southwesterly wind here, are common, are very similar between CLM and BATS, but you can see some local or mesoscale circulation. For example, in this way here, you have a river, that is Tietê River. And we can see that in CLM, we can note that there is less rainfall in the basin of the river. It's a big river. Then, for example, in BATS, this is not so clear. Here you can see also that in CLM you have more rainfall over center north of the city that is not so clear, that isn't in BATS scheme. Here I am showing the difference, the CLM minus BATS of 2 meters air temperature and the 10 meters wind and the rainfall. Here now it's clear that CLM is warm over São Paulo city, then BATS, and here you have also a valley, Paraíba Valley, where CLM is a little bit more warm than BATS. In the circulation, we can see that the southeast wind, this wind characterizes the sea breeze, that is a common phenomenon in São Paulo, and the difference shows the stronger northwesterly winds that they converge over the São Paulo city, and here you can note positive anomaly, more rainfall in CLM than in BATS. Exactly where the convergence of the sea breeze in northwest is occurring. This is another looking a local validation of the simulation. Here is the months, January to December. This is the monthly mean diurnal cycle. Here the time is in UTC. What I am showing here, this is the meridional wind. Negative is from north and positive is from south. You can see this is the observation. This one is what we have using CLM. This is with bats. You can see that the time of the change of the wind from north to south is very well captured along the year by CLM. Okay, the wind in CLM is also weaker than, for example, in bats. This can result that the fact that in CLM you are using the urban parametrization that can decelerate the wind. It's very interesting to look here. For example, you have January, more or less in October, there is a change of the time of the wind change from north to south, and this is very well captured by CLM, but not for bats. You cannot note this kind. But, so, I am finished. My final comments is we noted some progress in RegCM studies over South America. CREMA simulation are a very interesting experience to understand better what we can analyze, what we can go ahead in front using regional climate models. This CREMA simulation pointed the need of finding resolution to assess climate change impacts. A relevant point to when you are looking the regional simulation is the need of the use local mesoscale observation to evaluate physical processes in high resolution simulations. Now we are working in two main points. That is the flagship pilot study for South America, and that where you use the RegCM fine resolution over southeast of South America to understand extreme precipitation events. Erika told you yesterday that CREMA phase 2 is being executed by ICTP, and it will provide the 25 downscaling with RegCM 4.5 nested in three CMIP5 GCMs in various CORDEX subdomains, included in South America. Thank you.
Questions?
No.
Okay, no questions? Well, okay. Thank you, Rosemary.
Thank you.
Now we have the coffee break.
Ah, yeah.
Yes. So,
I forgot.
huh?
I
You
esqueci.
forgot about it. So, well, now we have the coffee break for a half an hour.
We are. We are on time.
Yeah? Yes, yes, we are okay. Yes. I need to go to the bathroom.
Oi, show. Tudo bem, e você? Você chegou agora?
Cheguei, fiquei lá.
Você vai poder ficar na reunião hoje?
Ela pediu para ficar, eu vou ficar um pouco, até metade. Assim.
Tá.
O pessoal pediu o carro para mais tarde, mas acho que você vai ficar até que horas? Né?
Não, você fica até que horas você puder.
Sì, sì.
Okay. Okay. Just I want to give an announcement. After these two talks, we are going to have the group photo outside. So please don't leave. Just wait there because we are going to take the group photo. Now, well, Erika is going to give a talk.
Okay, so it's me again. Now? Yes. Okay. If you can do convection permitting, you can turn on the microphone. Okay, so today the aim of the talk is to drive you a little bit about the history and status of the art of convection permitting climate modeling, because it's something quite new. And so the talk will explain first what is convection permitting, why do we need, when we speak about convection permitting, what do we mean, and how we do the convection permitting simulation for climate, and what are the problems, what are the advantages, what are the drawbacks, what are still the things that are missed because the community is not ready, okay? So to start with, this is a nice cartoon about what is convection, but I think all of you know. So we have convection when the atmosphere is unstable, and then we have this rising plume of moist air. So if you look at the distribution of precipitation all around the globe, you see that most of the convection precipitation is falling down in the tropics, as you see in the down part. But this you know very well since you live here. Do you? Okay. So it's changing. Ah, it works. Also the changing. Ah, I didn't understand. Okay, so when we need to model convection, we need to go to scale that are not resolved by the state-of-the-art regional climate model, nor from the GCM, because we have resolution that are too coarse to modeling the convection, right? So if we don't model explicitly the convection, then we have to use the parametrization that Graziano was illustrating yesterday. So we have some of the physical processes that are parameterized because we cannot resolve with the resolution that we have. When we speak about convection, we have to know that this is the main process that allows the vertical exchange between the lower and the upper troposphere, and for water vapor and for chemical species. So it's a process that is really important in the real life. But we also know that the convection, the parameterized convection, is the one that is the major source of error, especially for climate projection. This is just an illustration of the ECMWF IFS system. And so they plot here the contribution of each of these terms, so the dynamic, the radiation, the vertical diffusion, the convection, the cloud, and then you have the total. So this is the contribution to the adjustment of the temperature tendency. So how much the temperature tendency has to adjust every integration step. So this means how much error or uncertainty we have. And what you can see is that the convection is the one that play the major role. In fact, we have that 50% of the total forecast tendency is accounted for. The convection accounts for 50% of the total forecast tendency. So it's an important term, right? So if we are wrong with the convection, we are doing a bigger error compared if we are wrong with the, for example, the vertical diffusion, that it's only important than the lower part. So what we know also is that the parameterization in general are considered as a major source of error for future climate projection. But also the parameterization of the deep convection clouds is responsible for the largest uncertainty for projected any projection, both GCM and RCM. And there are many work that has been published on this topic, and this is still the case. I mean, there were many idealized experiments to quantify the amount of uncertainty due to this parameterization, and many are coming out. So the problem is it's there. Also, the other important thing is that the parameterized convection interacts with many other parameterization schemes, like, for example, the radiation, the PBL, the soil vegetation. So if we have a weakness in the convection, then we can also reach far through the non-linearity, and then we can propagate this weakness in other part. So this we saw already. So what we want to do is, so far we have not been able to do much because we were in this part of the diagram. But if we are able to lower our resolution and to cross this blue boundary, we may want to think that we can also not have a parameterized convection. So why we want to do this? What is the reason? Because we already know that having a coarse convection parameterization, we have a deficiency in the diurnal cycle. There are many work done on this. These are just few that are the most famous one. Then we have too much persistent light rain, this phenomenon that is known as a drizzle. So you see that the model is raining a little too often. And this is, it's important because when you look at like extreme, this is something that is important, because although the average precipitation may look fine, then when you go and look at the extreme, then things start to be a little bit more complex. Then we know that we underestimate the hourly precipitation intensity, so the maximum for the hourly intensity is underestimated. And also the tropical bias associated with the intraseasonal to interannual variability is mostly due to the parameterized convection, because of course the convection is a process that is dominant in the tropics. What we expect, so if we improve the representation of the fine scale orography and the surface in the surface field, this will be important for coastal, urban, wetland, and patchy cover. But also, this resolving this fine scale heterogeneity, so to be able to reach high resolution, is important for the forcing of the deep convection, right? So we don't want to go high resolution only because we better resolve this, but also because we can do these other things. Where do we expect the added value? Oh, sorry, this is the Mac Windows things. So where do we expect the added value if we do so? So where we can expect the added value? For sure, if we go to convection permitting scale, we can expect to have small scale extreme much better resolved. So for example, hailstorm, heat island, flash flood. In region with complex terrain, we can hope that we have a better snowpack, orographic precipitation and flow, better resolved. In convection dominated environment, of course, we expect to improve, but also we expect improvement if we want to look at the urban climate, hydrology, and energy, because this is the classical sector for the impact. So what do we need for the convection permitting modeling? So we cannot do convection permitting if we don't have a certain kind of ingredient. And the first ingredient is, as we learned already, we need to have a non-hydrostatic model. So we need to account for the vertical motion, otherwise we are lost in the beginning. Then we need, we cannot use a three-phase scheme, but we need to use something more complex for the microphysics. And with this, we already learned yesterday. So we need to have all these states here represented, and we need to model and have equation that represent all these arrow in the cartoon. So either this one or another one, it doesn't matter which. It would be the best in the reality would be to have a two-moment scheme that is a much more complex than this. But at the moment, this two-moment scheme is not yet a reality for climate study. How do we do this convection permitting climate modeling? We do in the same way as we do the regional, the regional climate downscaling, but there are other ways of doing it. So first, what we do is this: the limited area model are nested, and then you do multiple nesting. So you start from a coarse resolution, and then you go and zoom in, and you increase the resolution. So you do multiple nesting. You jump from a coarse to a middle resolution, and then to the high resolution. But you can also have some model, some global model, have a super parameterization. So they have like a cloud model inside the grid point. So they run for each of the grid point an explicit representation of convection. There are some global models that they say they run convection permitting, but these are just the Japanese, and they managed to run, I think, a week of simulation so far with the global things. And then we have the stretch model grid. So we have global models that are able to, within the global context, to zoom in on a region, and just for this region in which they zoom in, they switch off the convection parameterization, and they allow the model to develop its own convection process. What is the limitation? So far, the state of the art is that there are groups, as you learn, that are able to run transient simulation, climate simulation, so 150 years of simulation for domain like those one, with a resolution of maximum 12 kilometers. And the computer resource, it's okay. We can do this. We are able to do. I mean, there are centers that can do better or less better, but anyway, we can do. And if you go convection permitting, you have to imagine that running a convection permitting 4 kilometers, 150 years of simulation is something that, no, we cannot do. Not even the big center can do it. So even the big center like the Met Office or ETH, that is another one that has run the longest possible simulation in convection permitting, they still do it in time slice. So they just run like 10 years, 15 years, but not the transient. So this, at the moment, it's impossible for everybody. So it's, yeah, it's prohibitive. So what about the grid spacing? So if you speak about convection permitting, how high resolution you have to be? So which is the limit, the upper limit that you have to reach? So this question was already answered long time ago by this work by Weisman, and he demonstrated that the limit for the convection permitting model is 4 kilometers. So if you are below 4 kilometers, then you can think with it, if you have all the physical process in place to represent the convection. Above the 4 kilometers, there is this, what is called the gray zone. Between 4 and 10 kilometers, you don't know really what is happening. So the other important thing is that if we speak about convection permitting simulation, this is different from weather forecast. We don't want to do weather forecast because our models are not built for doing this. But we want to, and we don't want to simulate individual cloud system. This is not our target. Okay? We know that we know well that with at kilometer scale, the deterministic predictability is limited to a few hours. And then we have the stochasticity that is dominating the majority of the small-scale structure and process. So when we speak about convection permitting, we want to represent the statistic of climate, like we have been telling since yesterday. So what we aim to represent is the statistic of climate, and then also the statistic of the convection process. So for example, the convective element like diurnal cycle, average rainfall and precipitation intensity, interaction with the radiation, the Earth's surface, and the large-scale flow. This is what we aim to, okay, with our simulation. Then, what about the grid spacing? So how do we get to these 4 kilometers? So they were in the US. No, this is an experiment done over the Alps in 2012. And they were trying to understand what was the difference if I increase the resolution of my simulation. So they repeated exactly the same simulation in convection permitting at 4 kilometer, 2 kilometer, 1 and 0.5 kilometer. And then they looked at the water content of cloud within 300 by 350 kilometer square domain. And they look at the structure that were there. So what you can see that beside an intensification of the maximum of the structure, there is not much difference between those resolutions. They are very similar. There are no different structures that are forming at those resolutions. And also if you see the daily precipitation for just 1 month, this is July 2006, you see that there is not much difference. Same is true for the diurnal cycle. Okay, you see that like below 4 kilometer, all the rest it's more or less clustered around the same. So they don't behave different. You don't have any shift. You don't have any behavior that allow you to think that we should prefer 2 kilometer against 4 or 0.5. Okay. What about the domain size? So far, the domain size that have been simulated in convection permitting all around the world in many different projects are those one, the one that you see depicted. So the largest domain is this one in West Africa and in the US, but these are for very short simulation. Over Europe, we have the pioneer work done from the Swiss people on this little domain. Then we have this more coordinated blue domain, which many people are now trying to simulate the climate scenario at the convection permitting. And then something done in the US by the anchor people, essentially, that they start these things in the US. What about the model physics? Where are we? So the physics of the model for convection permitting is adapted from the weather forecasting model. So we are not discovering anything new. But at the moment, the setup are still not tested for climate. So this is really something new. So we have the process that we need to take into account is cloud, aerosol, radiation, turbulence, soil vegetation. And then if you look at the wavelength space, there is a space that where the convection permitting model are, that is called terra incognita from somebody, because these parameterization are still not adapted for the convection permitting model. Yeah. So but we know that, for example, to better resolve cloud, aerosol, and radiation, we need additional hydrometeors for convective cloud. For example, we should have Graupel in our macrophysical scheme, but we don't have yet. We need more microphysical scheme like the two-moment scheme, as I mentioned before, but they are not yet a reality for climate projection. What about the turbulence? There is not yet any theory for simulating the turbulence at this scale, and there is something done, there is some development done by those guys there, and they published already something in 2014, but it's not final yet. And also, we know that the treatment of the subgrid scale cloud, so the shallow convection, is not yet viable for this scale. So what we usually do, you run convection permitting, but you use still the parameterization for the shallow convection. So for the part of the convection that is shallow. And also, we also know that if you want to go to such high resolution, you also need to take care about the coupling of the land surface and the atmosphere. And also, this is still too coarse, so the parameterization of the land surface is still too coarse to interact with this kind of convection permitting modeling. And there is somebody looking at that. I mean, but this, the good thing is that the community is aware of the gap that we have to fill if we hope, you know, to improve this kind of simulation. But nevertheless, we have some result already. And so what we know at the present, we know that convection permitting modes do not necessarily represent better the daily mean precipitation. This is not what we want to improve, but we know that they are much better in the subdaily rainfall distribution. So like the diurnal cycle of the rain. So the diurnal cycle of the amount, intensity, and frequency of precipitation, it's improved. That there are many papers already published on this. All these simulations are not very long. So I told you it's like something like maximum 10-year simulation, but still they are consistent in showing the same signal. We know that the spatial structure of the rainfall and the duration intensity characteristic are better. So I mean, you have this organized convection that is developed in the right position, in the right time. And also the intensity of the hourly precipitation is improved together with the orographic precipitation. So there are already several studies showing this, telling that this is the way to go, and this is the direction to go. These are a few examples about the diurnal cycle. Here there are two simulations compared by all this crowd over there. The domain are several domains, so they kind of did a comparison, coordinated comparison paper. For each of the domain, no matter what it is, you have the observation in black, and then you have the convection permitting at 2 kilometers compared to the parameterized convection at 12 kilometers. And for each of the domain, you see that the convection permitting, the high resolution one, it's able to shift the precipitation peak according to the observation. So it shifts late in the day, so around 6 in the evening, the peak of precipitation. And this was a major drawback of the parameterized convection that usually has the precipitation peak much earlier in the day. So for all the domain, they manage to do this. Oops, sorry. They manage to do this, sometimes better, sometimes less. I mean, the comparison is not with the same model, so there are several models running on those domains, so it's not really consistent, but more or less everybody brings home the same message. Then the diurnal cycle, so there was a paper published by Berthoud et al. In which they compare this, the only existing so far long kilometer convection permitting simulation over Europe at 2 kilometers. One is from the UK Met Office and the other one is from ETH in Switzerland. And what they both find is that the amplitude and the phase, so the hour of the maximum precipitation in local time of the mean diurnal cycle, it's better if you go to convection permitting resolution. So you can see this compare the only, I mean, to be able to assess this added value, you need observations that are sub-daily. So you need hourly observation. And over Europe at the moment, the only available one are over the UK and over the Germany and Swiss. So if you compare just over this, the shape of the precipitation of 12 kilometers against 2 kilometers, 12 kilometers against 2 kilometers, you can see that in both 2 kilometers, this amplitude it's better represented. We don't know everywhere else in the domain. Same is true for the phase of the precipitation. So the time of, sorry, this is a little too small. So this is the time of the day from 0 to 24 p.m. And again, the observations are in the same place. So you see that when you move to the convection permitting, the violet color it's appearing and was not there before in the 12 kilometer. So there is a better timing and a stronger amplitude for the convection permitting in both cases. The same is true if you look at the extreme precipitation, but this is true for the, if you go to the sub-daily scale. This is one of the first paper published by Nicolina Ban from ETH. And what you see is that the convection permitting is able to improve, again, sorry for the mismatch of the title, is able to show an improvement when you are at hourly time scale, but when you move to the daily time scale, the improvement is not evident anymore. This is another example of extreme precipitation done with the same two twin simulations. So this simulation, they share the same domain. This is the average value of precipitation above the 99th percentile. And this is the comparison between, again, the 12 and the 2 kilometer. These are the 2 kilometer to compare with the observation. It's clear without any comments that these are matching better the observation and the location for both the intensity and the location. This is a Mediterranean intense event in autumn. That is usually the region, the season in which we get strong precipitation over here. In the Liguria, we have a lot of flash flood, and you see that this typical precipitation intensity is only represented here, and here is not there. Here is too much, and it's a little bit of messy.
UK is a regional climate model or is global?
No, this is a regional. This is a regional. It's a domain. It's a domain covering Europe. I have figures later on. Okay. The same message is the one from the this other. The same simulation, in which we see that they want to look at the contribution of to the total rainfall of the low intensity, moderate events, and intense events. So what is the contribution to the total rainfall, and compared to the observation? And again, you see the same thing. So the distribution. So look at this as a PDF, so the shape of the PDF of the precipitation. And you see once again that in this two column, the color are correct, more or less. In this other column, we are a little bit pitch-patchy. And then, okay, this was just a comment. Moving to somewhere else in Africa. So there is only one work done outside Europe long enough. So this is again the Met Office, and it's published just now. They did a Pan-African convection permitting climate simulation only for 5 years. And this is the domain for Africa. And in this case, they were running 4 kilometers, so a little bit coarser than the European case, because since in the tropics, the organized convection as a space scale that is bigger than in the mid-latitude, they show in the paper that 4 kilometers is enough to represent the convection permitting, the convection. So what the difference between this result and the previous one is that in this tropical, in the tropics, what we see is that at convection permitting, there is also an added value for the seasonal precipitation. So what they show here is the seasonal mean precipitation. So these are the observation. This is the this is the 4 kilometer model output. This is the bias compared to observation, I don't know which. And these are the bias of the 25 kilometer and the global model bias. So you see that in this case, also the seasonal representation, so the representation of the monsoon is better compared to the lower resolution. So we are also improving the time scale that is much longer compared to the diurnal. And the same is true over here. So this is the contribution of precipitation it's a PDF, it's a kind of PDF. So you have the observation from SIM over TRIM, both reported, because you know that in the tropics, the observation uncertainty is also an issue. And you see that the convection permitting one, so the giant one, the light blue, no, sorry, the dark blue is much closer to the observed PDF than the lower resolution. So still the things is confirmed at a longer time scale. And the same is true for the diurnal cycle, so it's consistent. So the added value of the diurnal cycle is consistent. So they divided Africa in these 6 regions that are over here, and they are comparing the diurnal cycle in local time. The observation in this case is TRIM, that has 3-hourly resolution. And what they see that is more or less everywhere you can have a shift of the maximum of precipitation only present when you run convection permitting. So we thought, okay, let's accept the gamble and let's try RegCM non-hydrostatic in convection permitting. So we did this also by ourselves, because we are involved in one of these projects. So we are running the model convection permitting over the alpine domain, the greater alpine domain that covers the whole Alps plus Italy, you will see later. And we did some case study to start with. This is just a cartoon, but also we tested the model somewhere else in the world. So we have at the moment working this in convection permitting. This is the domain, this is the great alpine domain, that is the domain that we use in this CORDEX flagship. Then we tested the model in Africa around the Lake Victoria, in the California coast, in the western US, and in the eastern part of the US, in the Great Plain, where often you have very intense precipitation events. We tested the model everywhere for short events, like 3-4 days, intense precipitation events, just to see if the convection was there. And only for this domain, we have longer simulation. And now, just out of curiosity, I show you how we are doing. So this is the case of the North California. It was a very intense event. You see that everything was flooded between 1680 February 2004. And we test the model over there. So these are the observation. This is what TRIM and chirps, so it's both observation merged together, are telling us. All the observation have differences. So these are a series of observation, and you can see that among them there are some differences, and also the reanalysis are different, of course, from the observation. If we compare our model and we look at how is the response at 12 kilometers against the 3 kilometers, for sure you can see that the 3 kilometer one is able to represent the events. And if we do have this shape of the precipitation, and if we compare the diurnal cycle of these two simulations, of course we see that the 3 kilometers is far better compared to the 12 kilometers in this event case. Another event is another case study is the northeastern Texas case. So it's over there. Again, these are the observations. So there is a kind of uncertainty among the observation. You can see that this secondary maximum is not present, for example, in one of the observations. In our simulation, we only compare. So this is our simulation. And we, in this case, nested directly into the era interim. The era interim was not showing anything for these events over there, but running convection permitting for these short events, we managed to reproduce the organized convection over there, and again, the diurnal cycle, it's okay. The other case study, the interesting one, is the Lake Victoria case study, because also there we are involved in organize in a organized project. So there will be more groups running the same simulation. The Lake Victoria, the convection over the Lake Victoria is very peculiar because you have a deep convection that develops during the night. And in fact, you have a lot of fishermen that are dead during the night when they go out and fish. And so we tried these events that was already present in the literature. Is the December 2009. You find a lot of paper published around this. And again, we are looking at different kind of observation. Again, please notice how different they are among themselves. And then we compare our lower resolution, the 12 kilometer, with high resolution. You see that the organized convection is developing just over the lake. We also have this maximum over the west coast that is shown by Seymour, not shown by SIRPS, by TRIM, but there is one observation that shows that. And if we look to a cross-section on the lake, this is the daytime, this is the night. You see how is the organized convection moving on the lake and reaching the maximum during the night. So we are really able to follow the events evolution for this particular case study. And then last but not least, this is the alpine domain. See, this is now just one example of 1 year long convection permitting simulation. We are running, now we are at the second year of the simulation. You can imagine that is a little slow, but still we want to show you some examples. So what we do here, we always compare the lower resolution, the 12 kilometer resolution, with the EOBS, that is a data set, observed data set at 25 kilometer. And then we have our 3 kilometer convection permitting resolution compared to the higher resolution data set that we have. That is a kind of patchwork of high resolution observation. So you can see that in all the seasons, so this is for DJF, March, April, and May. So if you compare the 12 with high resolution, you can have some deficiency. The 3 kilometer is a little bit better in the structure and the intensity. Look, for example, at the summer. We are able to depict the shape of the precipitation. We have this maximum over there. And compared to the lower resolution observation, of course, there is a big difference. The 12 kilometer is a little bit overestimating everywhere. This, and also the same is true as in fall, that we already learned this is an important season because we have a lot of precipitation happening over there. So our single year simulation, so it's not something that you want to look at just 1 year, but still, nevertheless, as the maximum of the precipitation while located over there, the structure is correct. The 12 kilometer is very messy. It's basically raining a little bit everywhere. And of course, the details are much better than the low resolution. And this is the literature if you are interested to start this research line. So if you want to, everything that is in the presentation you can find in the paper, and it could be a good source of information. Okay.
Hi, Erika. Very nice, impressive results with the convective permitting. Really nice. I was wondering, I have two questions. In the last results that you showed, how much of the improvement in precipitation comes from only resolution, like change from 12 to 5 kilometer RegCM without convective permission, I mean, convection permitting model? How much do you gain by only doing that? Mm-hmm. And the second question I had is, you only tested the model over land. What happens over the ocean? Does the convection permitting model improve also precipitation over land, over the ocean, or only over land?
Okay. So for the knowledge that we have at the moment, your first question is how much we improve only by doing the resolution or the convection permitting. So the answer is, if we didn't do the simulation and we only did in the past trials without using the convection permitting, what did happen if you use the parameterized convection at those scale? It's that you rain like hell. So my guess is that rainfall would be just largely overestimated due to the topography effect with the parameterized convection. So this is a like extrapolation of what I see. There is no study there yet. For your second question, the problem over the ocean are the observation, right? So if you go to such resolution, you really need high resolution observation. From what we read in the literature, the only things that is closer to your question is the representation of the monsoon in Africa. There, you see that the organized convection coming from the ocean, coming from the interaction with the ocean, is much better resolved and represented in time and intensity and space location. So also in that case, over the monsoon flow, you have an improvement. This is what the Met-Office is showing. But over the ocean per se, I don't know.
No, I was looking at that picture you showed, and if you look at in the South Atlantic and South Indian Ocean, actually I think the bias seems to be larger for the...
You mean the Africa case?
Yeah, in the Africa case, yes.
Let's have a look.
I mean, if you look at if you look at the Indian Ocean, and it doesn't improve at least. I don't know, maybe better.
Yeah, but I think
worse
you are comparing with the like GPCP or something over the ocean. So the resolution that the observation has over the ocean is very low. So I think the issue of this little blue point appearing is because, I mean, you don't have such a resolution.
So we can compare essentially.
No.
Okay. Hi. You mentioned that the double moment, you can use the double moment microphysics scheme, and that's because of computational cost or just computational cost? Okay.
Yeah.
No, thank you.
Two short questions. One is did you check the impact of the vertical resolution in each case event? And
yeah, the vertical resolution is also increased. I didn't mention, but when we go to convection permitting, we have to increase the vertical resolution to minimum 40 level. So in those simulations, we have 41 vertical level compared to the standard 1823 that we have in the hydrostatic simulation.
Right. And besides precipitation, is there any improvement of the convective permitting simulations on the, particularly for the turbulent heat fluxes? Did you check any improvement on this?
Not yet. No, we didn't check that, and there is nothing in the literature so far. So, but yeah. I think Silvina wants to ask something.
Thank you, Erika. It's impressive, really. But my question goes to the more methodological issue. I see that during the first stages of these convective permitting simulations, the nesting procedure was applied, but not now.
The what?
The nesting, the multiple nesting procedure.
It is
because these simulations are just driven by era interim reanalysis, isn't it?
No. The one in Africa, you mean? No, we always do the double nesting. So
you do? Okay.
We always do the double nesting. So if you remember the case study I showed from our model, is always jumping first to 12 kilometers and then to 3 kilometers.
Okay, so but you're showing...
there was only one case study in which we nested directly into the era interim because the 12 kilometers was just flat over there, and then we didn't see any improvement in doing the double jump. But in general, you have to jump. I mean, you have to keep the ratio of the resolution against
Okay, so your 12-kilometer simulation is in a bigger domain?
Yes,
So
the
a
12
much bigger
kilometer
domain, okay.
is over the Eurocordex, so we
Okay,
NAS
okay.
over the Eurocordex.
Okay, okay,
Yeah.
that was my question, thank you.
Hi Erika, thanks for your presentation. I have a doubt. You mentioned many steps that you followed to improve the capacity of rational climate model to simulate precipitation, such as lunar cycle precipitation. But do you consider to maybe improve the capacity or the interaction that have rational climate model with global climate models? Because if we analyze the variable of parameterization, it's a variable that it parameterized. So, the global climate model or the variable, the rational climate model that use from global climate model data, maybe influence in this part. So I don't know if you have some plans for that.
Yeah, we do have, and in fact, I didn't mention now because maybe it's not interesting for you, but we have a coordinated experiment done on this alpine domain. And one of the point, maybe I have it here, I can show you briefly. One of the point of this coordinated experiment is, it's slow. Yeah. The third aim of our project is possibly to first simulate the convection with some like lighter things, and also can we also feedback the finding that we have by running convection permitting to the global scale. So can we upscale our added value? Can we tell to the global model what is wrong in their parameterization of convection by doing this with a limited area model? So the idea is that there should be a feedback back to the global climate community saying that the finding will help them to refine this parameterization of the convection.
Thank you, Erika. Okay, the following talk is of Chou Sin Chan, sorry, from INPE here in Brazil.
Hello, I think, is it working? Yeah, okay. Yeah, well, hello. Good afternoon already. First of all, I would like to thank the organizers for the invitation, especially Rosemary and Tessio. It's a real big pleasure to be here and to be giving a talk here. I don't think I've done that before. Let me put this into. I'm going to mostly show what we have done in terms of runs, of outputs of the model. The ETA model is the model that I'm responsible for the development. And I have to acknowledge the team we have there in INPE. This is not a one person's work. It really requires a team. So I really have to acknowledge my team here. And then, well, the ETA model, the name of the model comes from the vertical coordinate. It's the only model that uses this is the point, approximately horizontal coordinate. All other models use the sigma terrain following coordinate. And the ETA coordinate tries to reduce the problems of derivatives near topography. So you can do more horizontal derivatives with reducing the errors. So the name of the model comes from this coordinate. So why we adopted Dieta at CPTech? So I know people from Argentina, this is in Chile. So we have the Andes here in the continent, which is a very steep and very high elevated mountain. It reaches about 7,000 near Aconcagua, in Aconcagua. This is the Caracoles. It rises from about 100 kilometers to about 3,000, 4,000 meters in 100 meters. So it's really steep on this side of Chile and a bit smoother, but it's not really smooth in Argentina side. So we have a steep topography here, and the coordinate in Neta is more appropriate. And there's been also work done by Figueroa, in which he showed that when we use the eta coordinate, the summer circulation South America is better represented than using sigma. So it's also a computation efficient model. So that's a reason based on scientific basis, okay, for using this model. So this is the general characteristics of the model. I highlighted in green parts of the changes that have been done, that have been inserted into the model through these years. We use the cut cell. It's not only plain. There's we call step mountains, but the mountains have cut cells, so the flux can go through some grid boxes and not only plain boxes, okay? There's some slope there. And it's a finite volume, fully finite volume model now, has been changed. And there has been other changes into the physics of the model. This is the dynamic downscaling that we have been doing recently. It was a request for the Brazilian national communication from the government. So we set up the domain here at 20 kilometers. It covers South America and Central America. There is a second nesting in southeast Brazil. And there has also been, there was a demand from Costa Rica, and we did also for Central America in 8 kilometers. The model was nested into 4 global models, HAGEM, Miroc, SM, and BESMI, the Brazilian. So just an idea of the global models, HAGEM, the British model, Miroc is the Japanese from the NIES, it's not written here, never mind. The Canadian Earth System model, and the Brazilian Earth System, which is developed in CPTech. So in general, they are about 200. Miroc is the one that had the highest resolution, but even though it's very coarse for impact studies. This is some kind of validation, evaluation of the present climate. So this is precipitation, 30-year mean, 30, can you see the pointer here? 30-year mean precipitation, millimeters per day. So these 4 models against CRU data. This is summer precipitation, this is winter. And in general, the models are different, but they all, this is eta nested into these global models. So the runs showed that there is this pattern of precipitation in the middle of the domain, most part of the continent. They are different from each other, and they're different from the observation, so there are errors there, but still they do capture this seasonal variation. The patterns of winter, for instance, this is an important point that for people that don't believe in long runs or downscaling or climate runs, and because we have in Brazil, so I always stress this, that all these runs that we produce, we do validate the runs. So we are not dealing with crazy models. But they're not perfect, and they will never be perfect. But at least there is some level of reproducing the climate pattern. And this is what we want in these climate runs, to reproduce the climate patterns. And these models do produce that. So that's why then we move to the future and we change these levels of concentration of gas, greenhouse gas concentration. But this is something that our community in modeling, we always show these present climate runs that we are able to reproduce with some level of errors, of course, but the general pattern of climate, it is reproduced there. This is also for temperature. Sorry, I didn't have the BASMI here. I was looking for the figures. And then we have these errors also that was identified in that Solman Silvina paper. There are some errors shared by some regional models, and here's the error. We noticed that with Mirac models, when there was more precipitation, the error in temperature was smaller in this region. So there are two errors here, precipitation and temperature. But it's something that we are still investigating how to reduce that. With the changes we have, we haven't been able yet to reduce this error. The error means the overestimate of precipitation in this region, around here in summer period mostly. Also, we evaluate some extreme. In general, we don't care much about changes in the mean, but the changes of the extremes are those, what we worry is more the decision makers. This is a work done by Scansi. I think she coordinated this work from this paper, and showing this trend, for instance, like this extreme precipitation. In general, here in south of Peru, there is some tendency of reducing the precipitation. Some areas here, there is some mixed signs of increasing and reduction. Very little observation over Brazil. But the models run, driven by RegCM, or CAM, or ESM, they have different signs as well for these extremes. For instance, like ETA driven by RegCM was doing an increase, this blue increase. And with BASMI and with Miracle, there was more reduction in Peru. Mixed sign here, there is some reduction, which is not comparable. But in BASMI, there is increase, increase. So the models, they do have different behavior. Although on the mean, the climatology is picked, but in terms of extremes, this is more difficult to pick. So some projections. So the runs were done from 2005 to 2006, when RCP starts rising, and up to 2100, actually 2099. But then we cut into time slices, 30-year time slices, because in general you don't have disk space enough to do a continuous run, or you have to stop and then restart the run. But then these are 3 time slices till the end of the century, and there are 4 models and 2 levels of emission scenarios, RCP 4.5 and 8.5. So higher emission and a moderate emission. So the idea is that you don't know which model is the best, and we don't know which will be the model that will respond better in different levels of CO2. You can see which responded better at the current CO2, but you don't know which model will produce the best response, because they have different sensitivities to CO2, and you don't know which one will respond better to the rising values of CO2, and you don't know which is the scenario that will happen, RCP 4.5, 8.5, and so everything is together among all these runs. So you look for a range that things may happen. a lower limit of the range, the upper limit of the range. So what we put here is the lower limit and the upper limit of change of precipitation for summer. So the lower limit starts from reducing precipitation in this first time slice in the central part of the continent, and there is already a little bit a hint of increasing precipitation here. Whereas if you go to the upper limit of the change, there is a large increase of precipitation in this area, so less increase, reduction of precipitation. So we're always looking into the lower limit and the upper limit of the change of all these options in terms of global, driven by global models and by RCPs. So as you move towards the end of the century, the things are getting even drier where it's drying, and even wetter where it is raining more. Okay, so this is an idea. This is in terms of temperature, the same thing, the lower limit of the range and the upper limit. So a little bit of warming and stronger warming, but they're all warming. That's the response. This is a run, we always have to do some run driven by reanalysis in order to check what are the errors that are coming from the regional model itself and not from the boundaries, from the global model runs. So this is diurnal, seasonal, annual cycle of precipitation in 4 regions. This is north, northeast, south, center, south. So in these 3 regions, and this is for temperature. And this is observations in black. So we notice that it's good to have, okay, and these are all different physics tests that we have been doing with the model. And those runs for the RCP, for the communication, national communication, use this version, -1. Blue -1. But we noticed that in general we were trying to look for, to envelope the observations. Okay. And another thing that I point at, in general with those runs using RCP, the winter season was, this dry period was ahead of time, like in June or May, the minimum. Whereas when we drive with error entering, this was not displaced. We do have the minimum of precipitation in the correct months. So most of that displacement in the seasonal run we had was coming from the global models. This is the run using for Central America, just show around. The demand, the request is because they have very narrow Andes around that area, very narrow continental width. So there was this request from Costa Rica. We helped to have these 8-kilometer runs. So vegetation, more detailed vegetation types of soil. This is to run, observation, model run, and the changes, future minus. No, it's wrong, minus present. And also in Central America, people are very much, the climate there is, weather there is very much worried about, controlled by these Caribbean low-level jet. So we looked into this jet. There are two years here cycle, they tend to show like that, 2-year cycle of the Caribbean low-level jet, and we noticed that there is a strengthening of the jet. This is published already. And this is the 5-kilometer, it's a non-hydrostatic version of the model running for climate. This is driven by RegCM. It's a second nesting. In the ETA, there is no rule, no requirement of ratio. You can directly nest into a course. But if you nest directly to a course, you will get very coarse information into your boundaries. So it is recommended to have some nesting in order to have more detailed information along the boundary. But it doesn't have this ratio number of 3 or 4 in it. You can use different ratios, depends on what you have available as boundary conditions. So this is 5 kilometers. This is what clean observation. You can pick the minimum of temperature over mountain areas, and the 5 kilometer in general picks up that better than, of course, 20. 20 kilometer, you don't have this value. We are around here. We don't see valley here when we run at 20 kilometer. So if you look into basin, small basin problems, you can't pick that with 20 kilometer. Also, mostly on the mean, the field is about the same as the course. But when we look into distribution, this is temperature distribution for São Paulo. There are one station for each metropolitan city of São Paulo. This is for precipitation. This is in logarithm scale because we wanted to stand out the extreme precipitation rates, like over 100 millimeter. When we look into 20 kilometer, it doesn't reach so much the high precipitation rates. This is observation. But when you go to 5 kilometer, the distribution approaches better to pick the extreme values. Also, the distribution improved. Not much change in Rio, but there is a lot of change in São Paulo and in Santos area. So the idea was to help to improve these extreme values. And also, we apply also bias correction when we provide data to users, in case they are not able to do, because you can always increase resolution. It's very nice to go into convection permeability scale, but that's very hard to do. So all models will have errors. So for instance, this is a mean over continent, and in general the model is cold. Even with projections, it still keeps colder than the observation. So the bias correction brings this feature of the annual cycle, these are the months of the year, and also it keeps these changes of temperature with respect to one time slice to the other. So just some examples in the energy sector, for instance, because when we increase the resolution, the idea is we provide more detailed information for impact studies. So this is a study of, there are 3 basins here, but I'll show just 2. This is Rio Grande, but the upper part of Rio Grande, it feeds into Paraná, which feeds to La Plata, but this is in Minas Gerais area. And also the upper part of San Francisco, which is also in Minas. Minas is a state which has a lot of topography, but it's also the state where lots of the basins, water comes from Minas Gerais. So the projections showed major reduction into the power supply, sorry, this is Portuguese, power supply. So there is strong reduction in many of these sub-basins of the upper Rio Grande, very strong, and going towards the end of the century. Every bar here, this is historical, and then every bar is 30-year time slice towards the end of the century. This is for the upper, Tres Maria, upper San Francisco. There's also reduction, most of it, on the 50 percentile. This is impact in agriculture. This is done by a colleague in Minas, in Brapa Milho. So this is the corn yield. Corn is very important production in Brazil. So corn yield in the baseline and in the future time slice using ETA, different RCPs. And with RCP 8.5, there's a stronger reduction in the corn yield. These dots are different, they do like that. If you sow at different dates, what's the production? Sowing at different dates. And using ETA driven by Mirac, the reduction is not so strong as using ETA hard gem. And this is for coffee. coffee is a very important commodity. And then this is mostly it's a agroclimatic zone for coffee. So there is an apt area, and towards the end of the century, the area that are appropriate or apt for coffee, they mostly climb the mountains. The area is reduced, and they climb the mountains. And this is production in different RCPs, and towards the end of the century, they will reduce. Mostly, the reduction is due to, in this area, is due to precipitation reduction. It was also developed a crop model for coffee. There are not many crop model for coffee actually, but this was developed and it was done inside the model. And because in this case, CO2 was taken into account. In an agroclimatic zone, CO2 is not taken into account, and plants, they grow more if they have CO2 available. So in the beginning, there was even some increase in production of coffee because of the amount of CO2 being available. But as the plant starts suffering more on temperature stress and precipitation stress, this production of coffee starts to decrease again. So it decreases again towards the end of the century. And in the end, these runs have been uploaded with the help from our colleague in SMHI, Gregory Nicolin. So parts of the runs of 20 kilometers are being uploaded in this ESGF CORDEX format. So you can look for RCM model and you'll find currently only temperature and precipitation are available on a monthly and daily basis for these models. But at the moment we're uploading also vertical levels. This protocol of SGF takes some time because it's not straightforward. You have to run some models and you have to have a lot of disk space to reformat those data into SGF protocol. So this is being done with the help of Gregory, really big help because they're providing the disk space and a person to help in this reformatting of the data. Okay, I think ongoing, I didn't show much of science, mostly of what we have done in terms of runs, but we are working on different land surface schemes, NOAA MP, multi-parameterization, and also inland model. And so we have been working with dynamic vegetation with those models, and also land use. We have done runs using 1 kilometer, 6-year continuous run. The purpose was to capture the fish bone patterns that there used to be in Amazon region. There used to be fish bone patterns because they were constructing, opening roads, and nowadays this fish bone pattern has been all merged into a big deforested area. So the period that was mostly highest rate of deforestation have been simulated over 6-year continuous using 1 kilometer runs. It is a lot of computer consuming, but because these deforested area, their patterns are narrow, it's not huge. In general, simulating deforestation have been used big, large patches and not realistic fishbone patterns. So this has been done, and I didn't show here, but it's being produced for publication. Also, we are putting chemistry into the model. This model used to be used for weather forecast, so chemistry used to be prescribed. And also for these long integration, the CO2 are prescribed. But the idea we are working with the chemistry transport put into it. Also, ocean models being coupled to it. Radiation scheme has been replaced. The weather forecast version used JFDL radiation scheme. Now the model has been replaced to RTMG, which is used widely. Many models are using RTM. It is actually pretty fast, and we have found that it's more flexible, or at least it allows to put more climate change factors into it. So that is being replaced already, but we are still working on it into coupling with deep convection. It's not coupling the scheme, but you have to look into how it interacts with the rest of the model. So this is something that's being done. And also there's a global version of the ETA model. It's under development. It's actually running, but we are now coupling to the ocean to it because we found it's more difficult to couple to the regional than to the global. So we are coupling the ocean model to the global version of the ETA model. It's a cubic grid. Instead of using E grid, we use B grid. But physics and the dynamics use the ETA coordinate, of course. And about the same. It's actually 6 regional models into a global model, because each face of the cube is a regional model. So it makes things easier for us to do in development. So some reference, and that's it. Thank you very much. Gracias. People are hungry. People are hungry.
They are hungry, yes.
Thank you, Xiao, for your presentation. In order to compute the climate change scenarios over South America, you mentioned that you use 4 global models, right? Why did you choose those models? Have you made a validation over South America of using those models?
Yeah. Well, in general, you try to run with what you have, but you check first. And we had other global models, but we checked. The RegCM performs well. No model is perfect, but performs well over South America. Morocco was doing reasonably. But in general, these 4 models, you had 2 with higher sensitivity. RegCM and Canadian are the 2 highest sensitivity, and the other 2 with lower sensitivity. So Morocco and BASMI, they have lower sensitivity. So in some way, you have to have some envelope of range of changes to open a bit and not go all the way to the same. So a little bit of that and a little bit of what is available near you. So among the models that we had at hand, we had I had several hard disks with global models written there, and then we checked, and so it's sort of that too higher sensitivity, too low. I would recommend, and to check if it's crazy completely. Okay.
So you show you show the best model for using CMIP5 protocol. Is this model being used to CMIP6?
I don't think so.
This model will participate of CMIP6? Do you know?
It is registered to participate. But
they are the people is running the CMIP6 simulation?
We are registered. BASMI is registered too, but we haven't had support to run.
Okay.
We need more people. We need more computer space. So this is not being provided.
No.
So far, no.
Okay.
But we should have already started if we want to. But we haven't yet. But I think they may start now because the BASMI model, they have, I think they have found one they have reduced a lot of the errors of the atmospheric part, I noticed. And I think it should be ready to start a new run. It should. But it needs more people to help that because it's really a lot of work.
So for temperature, lower levels has different behavior than the top of the mountain, so mid-tropospheric and upper levels. In your projection, you see this elevation warming effect that is now talking about more warming and accelerated effects over mountain region than shallow regions?
In some areas, but I think in general the larger pattern dominates. I didn't distinguish much over. There was some areas, I think over Central America, there was a little bit more. But in general, the model is colder, but the change in temperature, I think there was a little bit. We notice a little bit, I think, over the mountains, but I'm not sure. I can have a look. Can I have a quick look? Not these. It doesn't show. So I think what shows more is the continentality. In the inner part of the domain, the continent, is where warming is strongest. Also, like Canadian, the Ethernet into the Canadian is producing most of this warming into the western Amazon. But there is a lot of continentality. The inner part is warmer. Let me check this. I think the signal is more on continental. There is some something, but on the top of the mountain it's not very clear. I'm not sure where exactly is. I have to superimpose because I'm not sure if this is like on the slopes or on the top of the mountains. But there are changes near. There are changes, but I wouldn't be able to say if it's really on top of the mountain, but there are some changes.
Okay. No more questions?
Food.
Okay, well, thanks. Ciao.
Thank you. Thank you.
Don't leave. We are going to have the group photo now outside. Yes.